Welcome class to today's lesson on arithmetic sequences. Today we're going to be looking at the first type of sequence, which collectively is going to fit into arithmetic and geometric sequences for the chapter, and then later on we'll look at the series, which are sums of terms. But first now, I just want to introduce this topic with a bit of a visual picture for you here, this house of cards. I looked into this, and here's the Guinness Book of World Records holder for the tallest house of cards. Builds them one card at a time, but very painstaking. All right, so what I'm going to do here is I'm going to be, for different properties of this house of cards, I'm going to be looking at the sequence of the numbers and also the pattern of the numbers. So we're going to start with looking at the sequence in the rows. Well, that's really simple because the rows or stacks of cards just grow one at a time. So we would label them according to this sequence. The pattern is grows by adding 1. Okay, let's look at the number of triangles in each row. So we start with 1 triangle in the first row, 3 in the second row, 5. Each row below that has 2 more rows, 1 on each end. So how does this grow? This grows by 2 at a time, by adding 2. All right, moving on. Number of cards in each row. All right, well, if we look at the top row, has 3 cards. The row below that, can't count the bottom of the first stack in the second row. So really just looking at 6 cards in that second row, and then we're adding one more set of 3, goes to 9, and the one at the bottom below that going to have 12. So of course here it's going to grow by adding 3. Alright, so these are really simple patterns, really simple sequences of numbers. To introduce a challenging question, how many cards are in the bottom row? Well, without counting that, we would probably want to know which stack is the bottom row. We count them: first, second, third, fourth, fifth, sixth, seventh, eighth. Knowing that the bottom row is the 8th stack, and knowing that the number of cards in each row seems to be, we could kind of model it like this: 3 times 1, 3 times 2, 3 times 3, 3 times 4. We could therefore extend that and say, well, in the 8th stack we ought to have 3 times 8, or 24 cards. So there's certainly multiples that are being involved in this type of sequence, or we could also think of it as maybe put a little bit differently, a certain number of common differences which we could be adding to the very first term. .24 there would be something like 3 plus 7 threes. So a little bit of a pattern sets up here where we can look at the term number, which in this case is easily identified as the stack number, and we can relate that to the number of these common differences that we're adding. In this case, the common difference is 3. You need 3 more cards to make the next row. All right, let's tackle this in a little bit more formal way. You should have this handout as you're going through here, and what I want you to do is start with a simple pattern. Something, if you have Lego or blocks at home, you can do this, or you can just color it out. I'm going to start with a really simple arithmetic sequence, which has 3 blocks in the first stage or term, and then after that I'm going to continually increase by 2 more. So the next one's going to have 5 blocks, and the third would have 2 more than the previous, so we'd have 7, 4, 5, 6, 7. We could continue that further if we wanted to. This just gives us some numbers to go with. What we're going to try to do with this is establish the way we describe any term, or the nth term, the general term. It's another way also of describing that, of values in an arithmetic sequence. So stage 1 to stage 3 are shown there. Let's describe the pattern in words. Well, begin with 3 and add 2 more each time. So the rate of change is shown, the starting value is shown, and we could also tabulate this a little differently off to the side here. Just to illustrate this another way, we could use first stage, second stage, third stage, fourth stage, and just put the number of blocks that would be involved, and then as instructed here, calculate the first differences. So first differences would be clearly 2, and we can see that all the way through. We'd have 2, 2, 2. All right, now, at this point, you're probably looking at a formal definition for an arithmetic sequence. Well, formal definition in the textbook involves a couple things. The idea of a pattern, a sequence of numbers, and specifically related to a common difference. So that's what we could copy down for our definition. You can look to those pages if you want, and I'll just record it right now. All right, so there's a definition. An arithmetic sequence is a pattern of values which connect each term to the next term by a common difference. Now we give specific notation for these words. The first term, as in an alphabet starting with the letter A, is going to be term number 1. How many multiples that we are involving, we will relate to the term number, and the actual common difference itself is going to be letter D. So let's write those first 5 terms again of the pattern that I use. I started with 3, 5, 7, 9, the next would be 11. Rewriting them where each term is a sum of an initial value and a multiple of the common difference. Well, the first term, we don't add anything to it, so we'd add 0 2's. The next one, 5 is 3 plus 1, 2. 7 is 3 plus 2 2's. 9 is 3 plus 3 2's, and 11 is 3 plus 4 2's. Let's also focus in on the term number. So the term number here is 1, 2, 3, 4, 5. So what do we have? These values are our term values, and the ones below it are our term number. So the next step in this process is to analyze the pattern in the second version of the sequence, which would be this one here. So if we look at that one, we have first term plus number of terms subtract 1 times the common difference. And by number of terms, what we're really looking at is the term number. All right, step 6 in our worksheet has us creating a new arithmetic sequence of numbers. So we're not going to build it this time. I'm going to use, let's start with 2. And this time I'm going to use a common difference, which is a negative value. So I'm actually going to decrease by 4 at a time. So the next value would be negative 2. All right, so we want to be able to describe the general term for this sequence. Let's list what we know. We know that the first term, A, is 2. We know that the common difference could be found by subtracting any pair of consecutive terms. So we could, for example, look at negative 34 as the 10th term, and we could subtract the term before it, which would be negative 30. And we would be left with the common difference equals negative 4. All right, that's how we built our sequence. The general term would be first term plus number of terms, or in this case term number, subtract 1 times the common difference. Sometimes, as we come back to part B of number 6, we want to write this a little bit differently. We might want to write it as nth term equals first term plus common difference times n subtract 1, which makes it a little bit easier to simplify. So let's load in what we know. We know that the first term is 2. We know that the common difference is actually negative 4. And multiply that by n subtract 1 multiples. So if we simplify this, we're going to get 2 subtract 4n plus 4, which would, by combining like terms, give us 6 subtract 4n, or negative 4n plus 6, depending on what you prefer. So that's our general term for that sequence right here. Calculating the 100th term. Clearly we don't want to be adding negative 4 another 90 times. So we can just go right to the explicit formula, which is negative 4n plus 6, and we say we want to know 100th term. We're going to substitute as we would in function notation. 100 for our term number, and that would give us term 100, sub 100 equals negative 4 times 100 plus 6. So what we're kind of see happening here is we're going to be starting with 6, and we're going to be adding 100 multiples of negative 4, which would give us negative 400 plus 6 is negative 394. So that would be our 100th term. Last thing we might want to do here is look at is every multiple of our common difference going to necessarily be in the sequence? So kind of asking the question, multiples of d, x multiples of d, whatever those are those in the sequence? Well, let's see. We've got a multiple of negative 4 is our common difference. Let's take 50. 50 multiples of negative 4 is negative 200. Is negative 200 going to be in this sequence? Well, one way to tell is to assume that negative 200 is in the term, in which case we can model it after the general term pattern, which is negative 4n plus 6. Negative 200 subtract 6 would be equal to negative 4n. Subtract 6 from both sides up here. Okay, now negative 206 equals negative 4n. N would be equal to negative 206 divided by negative 4. That's the solution. And what is that answer? Okay, when we solve that, we get 51.5. Okay, so 51.5 is not a natural number, so that means that in that case, 50 multiples of negative 4 just doesn't fit into the sequence. So we have to be careful that we don't make that assumption. It kind of depends on what our starting value is. So negative 200 is not in the sequence. All right, some of the introductory questions have us writing the general term. Some questions are going to have us as a number 2, finding specific terms. This one, I'm not going to go through examples. Have we done enough of that before? It's pretty simple. If you wanted to find the 10th term, n is 10, and you're just going to substitute that in wherever you see n. Okay. Again, the first one is also pretty straightforward. This just involves substituting these into the general form a plus d times n subtract 1, and I've already shown an example of that in the previous activity, so I won't go over any from number 1 either. Okay, so in this video I'm just going to focus on the types that are a little more challenging, which are 3, 4, 6, and 7. So I'm going to go to our question slide here for number 3, and let's pick an example. We want to find the term in the arithmetic sequence that has a value of, and in this case, one example should be sufficient. Let's say 354. So we're assuming that 354 is in the sequence, which means we can model it after the general term pattern, which is that it's sum of first term plus a certain number of common differences, and the certain number is one less than the term number. So what we're really wanting to find is, what is the term number that corresponds to 354? Where is its location or position in the sequence? So let's substitute 354, and that's equal to, well, the first term is 4. A is 4. Common difference there is 7. We can see that. So it's going to be 7 times n subtract 1. So this is 4 plus 7n subtract 7 equals 354. So we'll solve this equation and we'll get our answer. Our answer, therefore, 354, is the 51st term. All right, so that's how we solve questions like number 3, determining where it's located in the sequence or its term number. Questions like number 4 determine the number of terms in each arithmetic sequence. This is just a little bit of a twist on question number 3, which is really having us solve the term number of, at this stage, the last term in the sequence. The current sequence can continue past that, but we're establishing the end of that sequence to be those 4 values. So let's look at, something that has maybe a negative common difference. All right? So a common difference sort of suggests subtraction, and sometimes we are actually subtracting values one to the next. You can think of it as adding a negative as well. So let's look at what we know for this sequence. First term is 8. The common difference is the difference between consecutive values, which is negative 3. Let's say for negative 172. So therefore, negative 172 is the 61st term. And that's what I was trying to determine. So and then said there are, or I could say that there are 61 terms in the sequence. All right, so we're going to finish off with just 2 more examples, looking at number 6 and 7. Determine the value of a and d in each of the following cases. This is a little bit different because we're given a bit of a spread in the terms. So we have, let's say for something simple like part C, well, we're given the 5th term and the 6th term. So if the 5th term is negative 1 and the 6th term is 1, well, they're right after one another. We're obviously adding 2 to go from negative 1 to 1, so our common difference must be 2. Well, that's easy. What if the terms, as in part D of number 6, differ by 6? Well, so we have 7 terms leading up to negative 55 as term 8, and then we have some more terms leading up to negative 73 as term 14. Well, keeping in mind how we solve for a general term, we get the 14th term would be the first term plus 13 multiples of the common difference. And the 8th term would be the first term plus 7 multiples of the common difference. So let's look at what is the difference between negative 73 and negative 55. Well, that would be negative 73 plus 55 would be negative 18. Well, what we've really just looked at is the difference between this and this. So if we were to write that as a plus 13 d's subtract a plus 7 d's, they both contain the first term, only a different multiple of the common difference. We would get a subtract a is no a's. 13d subtract 7d would give us 6 common differences, and that's of course what separates the 8th and the 14th term would be 6 common differences. So if 6 common differences is equal to negative 18, then one common difference would be equal to negative 3. And the last type of question which we could look at might have us going back to the idea of a recursive procedure, so a recursion formula. So let's take something like what we've just worked out. Well, we know that the common difference for this sequence is negative 3, and that would require that to get term 1, we could recognize that term 8 being negative 55 has seven common differences plus the first term. We know that common difference is negative 3. So that means that we're adding negative 21 to the first term to give us what? Negative 55. All right, well, solving for that, we would get A is equal to negative 55 plus 21, which would give us negative 34. So we know that the first term in the sequence is negative 34, and we know that the common difference is negative 3. Now let's keep in mind how recursive procedure works. Recursive procedure starts with initial term or terms. So we require term 1, which is A, which is negative 34. And the nth term is in general or explicit form first plus common difference times n subtract 1. But we could also say that for an arithmetic sequence, because they differ by a specific value that is added term to term, we could say that the nth term would be the term before it plus d, which in this case gives us nth term equals n term n subtract 1 subtract 3. Between that and telling us that the term 1 is equal to negative 34, that would be a recursive formula. That's where we'll stop today. Hope you have your note copy down and come in tomorrow looking to continue on the unfinished questions from the Blackline Master.